something extraordinary is unfolding above us. And it's not science fiction. September 2025 has turned into the busiest month for asteroid activity in modern history. One after another, near-Earth objects are racing past our planet. Some closer than the Moon. Asteroid 2025 FA22 just skimmed by at 5,000 kilometers away. Barely over twice the lunar distance. Only days earlier, 2025 RJ2 came even closer, slipping past at under 300,000 kilometers. That's less than the distance between Earth and the Moon. But these two giants are only part of the story. In the same week, nearly 30 other smaller objects zipped by within lunar orbit. Most were harmless. No bigger than a bus, the kind that would burn up or explode in the atmosphere like the Chelyabinsk event in 2013. Yet FA22 and RJ2 stand apart. At up to 120 meters across, each one is large enough to cause devastating regional damage if their paths had shifted only slightly. Behind the scenes, a global network of telescopes is catching this cosmic traffic in real time. In Hawaii, Chile, and Arizona, automated sky surveys scan the heavens every night. The new Vera C. Rubin Observatory in Chile, only months into full operation, has already changed the game. Its enormous camera captures wide swaths of the sky, flagging faint objects that older systems would have missed entirely. Every detection flashes across screens, triggering a chain reaction of analysis and tracking that plays out within hours. What's unusual is not just the closeness of these flybys, but their sheer number. Statistically, events like this should be once-in-decades outliers. Models suggest the odds of more than 25 close approaches in a single week are less than 1 in 1,500. So why is it happening now? Some scientists point to orbital resonances, or the possible breakup of a larger asteroid, scattering fragments along nearby paths. Others credit the surge to better technology, noting that detection efficiency for objects larger than 20 meters within lunar distance is now above 9. The truth may be a mix of both. Still, detection has limits. Asteroids approaching from the direction of the sun remain almost invisible until they're too close. A blind spot that cost us dearly when Chelyabinsk detonated without warning 12 years ago. It's this vulnerability that fuels speculation online. People post charts showing the sudden spike, asking if these passes are random chance or something else. A warning, maybe even a pattern. Scientists stay cautious, but they aren't dismissing the question. Every close call sharpens the reminder. Planetary defense is only as strong as the latest discovery. For a few tense days, the world's attention turns upward, and the unspoken thought lingers. What if one of these hadn't? A rock the size of FA22, 120 meters across, slamming into the atmosphere at 18 kilometers per second. The devastation would stretch far beyond the impact zone. If asteroid FA22 were made of the same stony material as most objects its size, it wouldn't even need to reach the ground to unleash destruction. The pressure of Earth's atmosphere would tear it apart in a violent airburst, detonating 10 to 20 kilometers above the surface. But this wouldn't be another Chelyabinsk. That 2013 blast injured over 1,500 people and shattered windows across 6 cities. FA22 carries more than 20 times that energy. The shockwave alone could flatten buildings across dozens of square kilometers, while glass, debris, and collapsing structures spread devastation far beyond the center. A searing flash of heat could set rooftops ablaze in seconds, leaving survivors scrambling for cover. But not all asteroids behave the same way. If FA22 were made of iron instead of stone, the outcome would be even more catastrophic. Iron asteroids don't fragment easily. Instead, they barrel through the atmosphere almost intact, slamming into the ground at nearly full cosmic speed. The result: a crater hundreds of meters wide, a fireball glowing across the horizon, and a column of dust and vapor hurled into the stratosphere. The local destruction would be immediate, but the ripple effects could extend for miles, crippling infrastructure and reshaping the landscape in minutes. And then there's the ocean scenario. With more than 2/3 of Earth covered in water, chances are high an asteroid like FA22 would strike at sea. The impact would vaporize water into a colossal steam plume and drive walls of water outward. Deep water absorbs much of the energy, but coastlines within a few hundred kilometers could face tsunamis tens of meters high. Ports, cities, and low-lying islands would be inundated before many residents even understood what was happening. The Chelyabinsk blast revealed the most frightening truth. We don't always see them coming. Objects approaching from the sunward direction slip past our telescopes, hidden in the glare until it's too late. Sergei Karpov, the man whose dashcam captured Chelyabinsk's fireball, still describes the chaos: windows exploding, confusion in the streets, people bleeding and dazed. Today he works with disaster response teams, reminding cities to prepare for events with no warning at all. His message is clear. The line between a harmless streak of light and a city-leveling disaster is razor thin. Simulations only drive the point home. A single asteroid's damage depends on size, speed, impact angle, and where it hits. Dense city, empty desert, or open ocean. It's not personal, not deliberate, just physics. Our only defense is vigilance, better detection, faster warnings, and systems capable of turning those warnings into action. Without them, the cost isn't measured in numbers. It's measured in lives and cities forever changed. And just as the world is processing this wave of asteroid activity, another celestial visitor makes its presence known. On September 11, 2025, a new comet, later named Swan, wasn't discovered by an optical telescope, but by an instrument aboard the ESO spacecraft, the Solar Wind Anisotropes. Swan instrument picked up a surge of hydrogen emissions, a unique ultraviolet signature known as the Lyman alpha glow. Before most observers on Earth had even aimed their telescopes, the comet had already lit up satellite data. Backyard astronomers scanning the Virgo constellation quickly confirmed what ESO had detected. Swan was brightening at an astonishing pace, its tail doubling in length in a single night. But it wasn't just getting brighter. Spectroscopic studies revealed a volatile-rich coma filled with hydrogen, cyanogen, and carbon compounds, a chemical cocktail that promised a rare and spectacular show. As Swan pushed toward perihelion, its activity skyrocketed in ways even veteran comet watchers didn't expect. Instead of water vapor dominating, hydrogen was pouring out at staggering rates. The culprit was Swan's fragile nucleus cracking apart under the heat of the sun. Each fracture exposed fresh ice, releasing hidden gases in sudden violent outbursts. Instruments tuned to ultraviolet light caught these hydrogen flares, painting a picture of a comet under extreme stress. Professional observatories quickly shifted gears. The Vera Rubin Observatory, still calibrating its survey schedule, rushed to track the rapidly changing coma. Meanwhile, amateur astronomers across the world kept the data stream alive, logging brightness changes, mapping the evolving tail, and reporting outbursts in near real time. Their alerts guided larger telescopes, ensuring nothing slipped through the crack. High-resolution spectrographs captured fleeting details, jets of gas arcing from the core, subtle changes in chemistry, even the stress signatures that often signal an imminent breakup. By late September, models showed Swan might not survive its solar encounter at all. If its fragile nucleus gave way, the debris cloud could create a dazzling spectacle, visible not only to telescopes, but to the naked eye. For planetary defense experts, Swan's behavior was a sobering reminder. Sometimes threats don't creep silently across the void. Sometimes the warning arrives as a sudden flare, and it's the global web of amateurs and professionals working together that makes the difference. While Swan kept the skies unpredictable, humanity's eyes were already fixed on another date. April. That's when Apophis, one of the most infamous asteroids ever discovered, will pass just 32,000 kilometers from Earth, closer than many satellites. Bright enough to see without telescopes, Apophis will sweep across the night sky in an event unlike anything in living memory. When it was first spotted in 2004, headlines branded Apophis a planet killer. For a time, the possibility of impact felt terrifyingly real. But improved calculations eventually ruled out collision. Instead of fear, the flyby now offers an unprecedented scientific opportunity. A live stress test for planetary defense. As Apophis grazes past, Earth's gravity will pull on it hard enough to trigger landslides, shift loose dust and rock, and maybe even alter its shape. These tidal effects have never been observed on a body this size, and no lab experiment on Earth can replicate them. To capture the changes, NASA is deploying OSIRIS-APEX, a spacecraft designed to rendezvous with Apophis soon after its flyby. It will document every boulder shift, every scar, every mark of Earth's invisible grip. For Andrea Riley, a systems engineer on the mission, the event carries personal meaning. She remembers being a teenager in 2004, watching the news as the world debated whether Apophis might hit. That mixture of fear and fascination shaped her path into planetary defense. Now, 2 decades later, she's part of the team that will transform that old dread into discovery, turning what was once a doomsday headline into one of the greatest learning opportunities in asteroid science. When Apophis makes its pass, it won't just be another cosmic flyby. It's a full-scale rehearsal for humanity's ability to defend itself against real celestial threats. Every calculation, every radar ping, every line of code uploaded to Osiris Apex is part of a global experiment in preparedness. Instead of panic, scientists want precision. Instead of fear, they want knowledge. What once made headlines as a planet killer is now shaping up to be the greatest live demonstration of planetary defense in human history. The entire world will get to witness how far we've come in turning danger into discovery. But while Apophis tests our defenses, another visitor is rewriting the rulebook entirely. Cataloged as CC 2025N1, or 3I Atlas. This interstellar comet stunned astronomers the moment Pan-STARRS flagged its path on July 1st. Unlike typical comets, which gush water vapor, Atlas breaks the trend completely. Data showed its coma bursting with carbon dioxide at an astonishing rate, 29 kilograms every second, while water barely trickled out at just 6.6 kilograms per second. That's a nearly 20-to-1 ratio, the exact opposite of what's expected. And that wasn't the only anomaly. High-resolution spectra revealed nickel pouring off the comet without its usual partner, iron. In nearly every comet we've ever studied, those two elements travel together, liberated by the same heating processes. Here, iron was practically missing in action. Scientists are debating, why did Atlas form under unique conditions? Did cosmic rays strip away its iron compounds during billions of years wandering the galaxy? Or could this be the first real evidence of nickel-rich organics breaking down in deep space? Nobody agrees yet, but the arguments are fierce, and the data keeps coming. Then in mid-August, things got even stranger. The Mars Reconnaissance Orbiter spotted a massive outburst, doubling the comet's brightness in just 3. Ground-based telescopes quickly saw the tail split into multiple streams, dust shooting off in different directions. Unlike the familiar water-driven jets, these flares hinted at carbon dioxide pockets exploding as sunlight cracked open the comet's surface. Adding to the mystery, light curve analysis showed Atlas rotates in a slow, almost drunken tumble, with a period stretching over 22 hours. Its shape appears nearly spherical, or perhaps irregular in ways that make predicting its behavior nearly impossible. Each observation uncovers more riddles, and with perihelion approaching on October 29th, astronomers are scrambling to capture as much as they can before it vanishes behind the sun. For now, 3I Atlas isn't just another comet. It's a messenger from the farthest reaches of the galaxy, carrying chemical signatures and cosmic scars that challenge everything we thought we knew about how worlds form and evolve. It's slow spinning, unpredictable, and unlike anything ever seen in the solar system.